All right, let's talk about one of the most fundamental building blocks in all of electronics, the common source amplifier. We're going to go way beyond this simple textbook formula. We're going to start with an ideal model, push it until it breaks, and in doing that, we're going to uncover the absolute physical limit on how much gain you can ever get from a single transistor.
So, here's the game plan. First, we'll walk through the standard, by-the-book analysis procedure. Then, we'll go on a quest for more gain and see exactly why our simple approach just, well, it falls apart. That's going to force us to find a more realistic model, which, and this is the cool part, will reveal the ultimate intrinsic gain limit of the device itself.
Okay, first things first. To make sure our circuits actually work, engineers follow a really specific procedure. So let's walk through the rules of the game for analyzing this thing correctly every single time.
Now, in a perfect world, the voltage gain is beautifully simple. It's just two things multiplied together. RD, which is our load resistor, and GM, the transistor's transconductance. You can kind of think of GM as a control knob. It tells you how good the transistor is at turning an input voltage into an output current. The bigger the GM, the more gain we get. But, as you'll see, this simple formula is hiding a few secrets.
Analyzing any amplifier really follows this critical path. First, you have to figure out its DC operating point, its steady state. Then, you make a huge assumption about how it's behaving, which lets you find all the small signal stuff and calculate the gain. But then, and this is the part you absolutely cannot skip, you have to go back and prove that your initial assumption was actually correct.
Okay, enough theory. Let's ground this with a real example and plug in some numbers. We've got a 2-volt supply, a 3 kilo-ohm resistor, and a pre-standard transistor. Let's see what happens.
So, here's that crucial step I mentioned. We have to assume the transistor is in its saturation region. That's just the fancy term for the mode where it actually acts like an amplifier. If it's not in this region, it's basically just a switch, and all our calculations are totally worthless. So we make the assumption now, but we've got to circle back and check it.
So, with that assumption in place, a little bit of math tells us we've got a steady DC current of 245 microamps flowing through our transistor. Think of this as the baseline, the quiet state that our little input signal is going to wiggle up and down.
And now for the moment of truth. Let's check our work.
The rule is simple. For the transistor to be in that happy amplification zone, its drain-to-source voltage, VDS, has to be bigger than 0.7 volts. We calculated 1.265 volts, which is safely above the line. Whew! Okay, our assumption was solid. The amplifier is biased correctly.
So after all that, we can finally calculate our gain. And it's just over 2, which, let's be honest, is not great. I mean, it works. It makes the output signal twice as big as the input, but in the world of electronics, we often need gains in the hundreds or even thousands.
Yeah, a gain of 2 just isn't going to cut it for most applications. So the obvious next question is, how do we get more? And this, right here, is where our simple little model is going to start to fall apart.
Well, if we look back at our formula, AV equals negative GM times RD, there are really only 2 knobs we can turn, right? We can crank up the resistor, RD, or we can try to boost the transistor's transconductance, GM. So, which path should we take?
Let's try the easy way first. If we want to double the gain, it seems obvious, right? Let's just double the resistor from 3K to 6K. Simple. What could possibly go wrong? Well, when we go back and rerun the numbers, we run smack into a huge problem. Because we have more resistance, we get a much bigger voltage drop across it. That means there's way less voltage left over for our transistor. Its VDS has collapsed all the way down to just 0.53 volts.
And this shows the problem perfectly. Our new VDS, 0.53 volts, is now below that 0.7 volt limit we needed to stay above. We've pushed the transistor out of the saturation region and into something called the triode region. It's not an amplifier anymore. It's just a resistor. We've actually killed the gain we were trying to increase.
So here's the takeaway. When you have a limited power supply, you can't just keep increasing the load resistor to get more gain. You run out of what we call voltage headroom really fast, and the whole thing just stops working. Our hands are tied.
Okay, so that was a dead end. What about the other knob, increasing GM? Well, we could try to push more current through it, but that just creates the exact same voltage drop problem we just saw. Or we could make the transistor physically bigger, but that adds all sorts of other problems that hurt its performance at high frequencies. So yeah, it seems like we're totally stuck.
The fact that our simple model led us to a dead end can only mean one thing. Our model is too simple. It's time to add a bit of real-world physics into the mix to see what's really going on.
And the main culprit is this effect called channel length modulation. The short version is that an ideal transistor is a perfect current source, but a real one isn't. A real one is a little bit leaky, and we can model this leakiness as a small internal resistor, which we call RO, that's built right into the transistor itself.
Now check out how this changes our gain formula. This new internal resistor, RO, shows up in parallel with our external resistor, RD. And here's the thing about parallel resistors. The total resistance is always less than the smallest individual resistor. This means our real-world gain will always be less than what our simple, ideal formula predicted.
This really drives home a powerful rule of thumb. The gain of this amplifier is always going to be negative GM times the total resistance it sees looking out from its drain. This new resistor, RO, is just part of that total picture now, and it's always there pulling the gain down a bit.
So this new, more realistic model, it reveals this fundamental limitation, but it also lets us ask a really fascinating question. If we can't just keep making our external resistor bigger and bigger, what is the absolute theoretical maximum gain we can ever hope to get from just one single transistor?
To figure out this ultimate limit, let's do a little thought experiment. Looking at our new formula, what would happen if we could somehow make our external resistor, RD, infinitely large? What would be left?
Well, if RD becomes infinite, the math simplifies beautifully. The total resistance just becomes ρ. So the absolute maximum gain is just minus GM times ρ. We call this the intrinsic gain. It is the performance ceiling of the transistor itself baked into its own physics. You literally cannot do any better than this with a single device.
And here's the real kicker. For a modern, tiny transistor, that fundamental intrinsic gain, it's often only around 5 or 10. That's it. That's the best it can ever do. So that leaves us with one final huge question. If our basic building blocks are this limited, how on earth do engineers build amplifiers with gains of 1,000 or 1,000,000? Well, the answer involves some very clever circuit design, and that's a story for another time.